In the silent cold of deep space, a signal arrived that should never have existed. The James Webb Space Telescope detected returning light from 3I Atlas, but the light was coming from angles that geometry itself forbids. A reflection with no lawful path, a glimmer that defied every rule of optics. For decades, astronomers trusted the certainty of reflectance physics. Light travels, light strikes a surface, light returns along predictable routes shaped by angle and motion. But when Webb focused its high-resolution gaze on 3I Atlas, those rules bent. The observatory recorded reflectance signatures emerging from directions that did not match any known entry path. No rotation pattern, no surface irregularity, no natural scattering could produce the angles Webb measured. It was as if the object had answered with light from an invisible place in space. This was not noise. This was not sensor error. The timing aligned, the wavelength aligned, the profile matched the object, but the geometry refused to make sense. Reflective surfaces cannot return light from non-existent angles. Yet something out there just did. In the control rooms and data labs, analysts stared at the graphs with a mix of disbelief and unease. Every data point insisted on the impossible. Every model failed. Every known law produced silence where the signal should have been. The forbidden angle reflectance was real. Across the scientific world, a new tension began to rise. If Webb was right, then something about 3I Atlas was sending light in ways no natural structure should allow. If Webb was wrong, then the most advanced space telescope in human history had just delivered a ghost reading. Either answer carried weight. Tonight, we step into that mystery, into the paradox born from a single beam of returning light, into the investigation that now challenges the very geometry of observation itself. The story of 3I Atlas began quietly, almost anonymously, in the steady rhythm of automated sky surveys. It was first flagged by a wide-field detection grid scanning for transient objects near the boundary of solar space. At first, it looked like any small interstellar traveler drifting past the outer planets. Dim, unremarkable. Barely more than a moving point of light against the black. But the early trajectory showed something unusual. 3I Atlas was entering the solar system on a shallow incline, not steep, not grazing, but angled in a way that hinted at long-distance travel through interstellar dust. Its brightness curve didn't match a typical comet. It didn't match a rocky fragment. It didn't behave like ice. It didn't behave like metal. It simply glided inward with a reflectance profile that seemed too smooth, too stable, too controlled. Teams compared it to Oumuamua and 2I Borisov, the first two confirmed interstellar objects ever seen. But 3I Atlas was different. Its brightness didn't fluctuate the way a tumbling shard would. Its spectrum held sharp edges that resembled engineered surfaces. Even so, nothing about it truly violated physics. Not yet. The decision to involve the James Webb Space Telescope came from a combination of curiosity and caution. Webb carried instruments capable of reading fine-grained reflectance at distances older telescopes could barely resolve. If 3I Atlas held secrets in its surface, Webb would extract them. If the object was natural, Webb would confirm it. If not, the data would speak for itself. The first scheduled observation window opened when the object drifted near the plane of Earth's orbit. Webb aligned its mirrors, locked onto the faint target, and began a series of high-resolution reflectance sweeps. No one expected trouble. No one expected paradox. The intention was simple. Measure the light, measure the angles, build a surface model. But as the raw data streamed back to ground teams, patterns began to diverge from the predicted geometry. Return angles didn't match the incidence angles. Some of the reflected light appeared to originate outside the plane of observation entirely. It was a small anomaly at first, barely noticeable, a whisper in the numbers. But with each pass, the anomaly grew sharper, clearer, more defiant. Soon, analysts realized they were not looking at random scatter or glare. They were seeing structured reflectance arriving from directions that physically did not exist in Webb's observation frame. Every new data set added weight to the impossible. 3I Atlas was sending light back along paths no natural surface should create. Astronomers revisited the history of unusual reflectance events. None matched what Webb recorded. No asteroid, no comet. No interstellar visitor had ever returned light from forbidden angles. The paradox was now fully seated in the story of this object. Why did 3I Atlas reflect light this way? What kind of surface creates signals from non-existent geometries? And why was the effect only visible when viewed through Webb's unparalleled resolution? Those questions drove scientists deeper, into older observations, into simulations, into theories that stretched the limits of known physics. But every path led back to the same point of origin, the moment when Webb first turned its attention to 3I Atlas. To understand the strangeness of the forbidden angle signals, we have to start with the simplest idea in optics. Light behaves. It strikes a surface, it bounces away. The angle of incidence equals the angle of reflection. This rule holds from polished metal to frozen ice to the dust grains drifting between the stars. Even chaos respects it. But when Webb measured the reflectance of 3I Atlas, that foundational rule fractured. The telescope emitted no light of its own, yet it captured incoming photons from directions that did not align with any known path of origin. Imagine shining a flashlight at a mirror and having the reflection return from behind you or from a point above the mirror where no surface exists. That was the nature of the anomaly. Webb's high-resolution instruments rely on precise geometric mapping. Every returning photon is compared to a dense lattice of angles, orientations, and predicted pathways. When the forbidden angle light appeared, it did so with mathematical confidence. Its position was stable. Its wavelength was coherent. Its timing matched the rotation curve of 3I Atlas. Yet the origin point sat outside the legal geometry of reflection. Scientists began with the simplest explanation: scattering. Rough surfaces can disperse light in wide patterns that sometimes appear counterintuitive, but scattering produces noise. It produces soft edges. It produces randomness. The anomaly on 3I Atlas was none of those. Next came the idea of subsurface reflections. Light can enter a material, bend inside it, and emerge at odd angles. Crystal ice can do this. Certain minerals can as well. But subsurface bending leaves spectral fingerprints. It stretches the wavelength. It warms the signature. The forbidden angle photons were pure, untouched. They held no sign of internal travel. Then came the engineered surface hypothesis, a structure shaped to redirect light intentionally, something like a microprism grid, or a curvature designed to reroute incoming energy. But this required precision beyond what a drifting interstellar object should have. It required alignment. It required purpose. And most importantly, even engineered redirection still obeys geometry. It cannot return photons from angles that do not exist in the observation frame. So researchers turned to a more daring interpretation. Perhaps the object was not reflecting light at all. Perhaps it was re-emitting it. In this idea, incoming photons strike a surface, trigger some unknown process, and new photons are released at different angles. But the timing betrayed this theory. The forbidden angle photons returned too quickly, far too quickly. There was no measurable delay between the incident and the return signals. It behaved like pure reflection, but impossible reflection. Computer simulations eventually revealed a strange pattern. The forbidden angle light seemed to shift with the rotation of 3I Atlas in a way that suggested hidden geometry. It was as if the object possessed structures that did not align with its visible shape, surfaces that Webb could not see directly, angles that did not match its silhouette. Light was returning from these invisible faces, yet no scan had ever revealed them. Imagine an object with more faces than its physical form allows. Imagine a geometry that hides itself from every viewpoint except through its reflectance. That was the conclusion the models hinted at. 3I Atlas was acting like a shape that did not fit within three-dimensional space. A surface you could map in light, but not in structure. A geometry that rotated into and out of visibility depending on how photons struck it. It wasn't violating physics outright. It was bending the dimensional rules that define what a surface can be. The James Webb Space Telescope had not just captured unusual light, it had captured a clue to a deeper structural truth about the object, a truth that brought scientists face to face with a more profound question. If an object returns light from forbidden angles, What does that say about the shape of the object itself? The deeper scientists pushed into the data, the stranger 3I Atlas became. Every new reflectance sweep revealed patterns that resisted natural explanation. What began as a single anomaly soon unfolded into a tapestry of paradoxes, each one more unsettling than the last. The first strange fact came from rotational timing. The forbidden angle signals did not appear at random. They emerged only during specific phases of the object's slow spin. These windows were narrow, precise, predictable, like a lighthouse beam that reveals a hidden structure only when the angle is perfect. But no visible feature on the surface matched those timing intervals. Nothing on the exterior of 3I Atlas rotated into view that could explain the phenomenon. It was as if the signals were linked to a surface that turned with a rhythm separate from the physical rotation itself. Then came the spectral paradox. When Webb broke down the wavelength of the forbidden angle photons, it found they matched the original incoming light with uncanny precision. No stretching, no warming, no absorption, no internal travel marks. In natural materials, even the smoothest reflectors alter the returning light slightly. But these photons looked untouched, pristine, as if they had avoided contact with any real surface at all. A third mystery emerged from cross-analysis with earlier space telescopes. When researchers scanned archive data from the Hubble Space Telescope, they found faint irregularities that hinted at the same behavior, but far too weak for anyone to notice at the time. But these earlier glimpses shared one detail. They aligned with the same rotational phases detected by Webb. The forbidden angle effect was not new. It had been happening for years. Only Webb had the resolution to expose it fully. This raised a question no one wanted to say aloud. Had 3I Atlas always possessed this impossible geometry, or had something activated it only recently? Even more unsettling was the angular displacement itself. Some of the returning photons arrive from directions that lay outside the object's own physical outline. If you trace their trajectory backward, they pointed to empty space. Not the surface, not the limb, not any feature detectable by infrared imaging. The light returned from nowhere, a nowhere that moved with the object. Another detail emerged from brightness modulation. At certain rotational speeds, the forbidden angle reflections intensified sharply, then vanished without transition. It was too clean to be natural, too sudden, too binary, like a switch. Some teams proposed the idea of microfaceting, tiny reflective tiles across the surface that might align in rare configurations. But the surface scans showed no sign of such structures. No grid, no pattern, no texture. The object was smooth, almost unnaturally so. Then came the strangest paradox of all. The forbidden angle signals obeyed an internal symmetry that did not match any known three-dimensional shape. The angular spacing between bursts followed a repeating ratio that belongs to higher dimensional geometry, not in a metaphorical sense, in a strict mathematical sense. The pattern resembled projections used in theoretical physics when describing four-dimensional surfaces collapsed into a three-dimensional view. To astronomers, this discovery felt like standing at the edge of a map that showed coastlines from another world, a geometry that did not belong here, a structure that hinted at dimensions our senses cannot see, but that light somehow could. Some researchers proposed that 3I Atlas might be a fragment of a larger interstellar object that once possessed impossible geometry. Others wondered if it could be coated in a material that manipulates incident photons in ways we have never observed. But none of these theories survived contact with the data. Every explanation demanded changes to physics so extreme that they collapsed under their own weight. Then a radical idea spread quietly through late-night meetings and encrypted emails. What if the object was not reflecting light at all? What if it was predicting light? A surface that responds not to the photons that strike it, but to the photons that are mathematically possible within the observation frame. A surface that answers potential light paths, not actual ones. This would mean the forbidden angle reflections were not echoes of light from our universe's geometry. They were echoes from the geometry of what could exist, but does not. A form of reflective probability. A surface returning answers from unreal angles. A final anomaly deepened the mystery. During one of Webb's longest observation runs, the forbidden angle signals briefly synchronized with a subtle shift in the object's thermal signature, a shift that should not correlate with reflectance at all. It was faint, barely measurable, but its timing was perfect, as if the object adjusted itself in response to the incoming light, as if it reacted, as if it sensed. The discoveries of Part 4 left one undeniable truth hanging over every research team. 3I Atlas was not behaving like a passive object drifting through space. It was behaving like something built, something purposeful, something shaped by a design philosophy far beyond our understanding of geometry and optics. In the wake of the forbidden angle discoveries, the scientific world found itself standing at a threshold, a boundary between what humanity has always assumed about light and what 3I Atlas now forced us to reconsider. The implications stretched far beyond a single interstellar object. They reached into physics, engineering, and our understanding of dimensional structure itself. Every unanswered question became a doorway into a possible future. The first impact came in the field of optics. Engineers realized that if 3I Atlas could return photons from angles that should not exist, then reflectance might not be limited to three-dimensional geometry. This idea challenged hundreds of years of design principles. What if a surface could bend the mathematical frame in which light travels? What if a material could interact with photon paths not as fixed lines, but as probabilities? Such a discovery could transform every optical technology on Earth, from telescopes to satellites to sensors to communication systems that rely on laser precision. A single breakthrough in forbidden angle reflectance could change entire industries overnight. Photon routing came next. A surface that predicts and re-emits light paths could become the ultimate stealth technology. An object could appear invisible to any detector that relies on predictable reflections. If the returning photons emerge from angles you cannot see, then the object becomes untraceable. Not by cloaking, not by absorbing light, but by answering with geometry you are unable to measure. Military and aerospace researchers quietly took notice. If 3I Atlas held the secret to impossible reflectance, then the future of reconnaissance, detection, and signal mapping might be rewritten. But the greatest implication came from physics itself. The forbidden angle phenomenon forced scientists to confront the possibility that 3I Atlas was not structured entirely within our familiar three-dimensional world. Its shape, its reflectance, its hidden geometry, all pointed toward a surface that behaved as if it existed partially outside our spatial frame. Not in a mystical sense, in a mathematical one. A four-dimensional or higher-dimensional projection could produce the reflectance patterns Webb observed. A shape that cannot be fully seen, but can be detected through the way it handles light. If this interpretation is correct, then 3I Atlas becomes the first physical evidence that higher dimensional objects can pass through our universe without disintegrating. It would mean that dimensional boundaries are not barriers, they are interfaces, and that matter shaped in a deeper geometry might interact with light in ways that defy classical rules. Such a discovery would force new branches of theoretical physics, new cosmology models, new ideas about how structures form in interstellar space, and perhaps new ideas about what intelligence in the universe might look like. Scientists also considered the possibility that 3I Atlas could be a probe, not active, not guided, not communicating, but designed with a purpose so long-lasting that even after traveling for thousands or millions of years, its geometry still performs a function we cannot yet interpret. A probe that measures space by bending the rules of reflectance. A probe that reveals its structure only when struck by the right light at the right angle. A probe that carries information encoded not in radio, but in geometry. If this is true, then the forbidden angle signals captured by Webb might be more than anomalies. They might be messages, not written in words, but in dimensional behavior. A kind of optical language, a language built into the shape itself. The European Space Agency, NASA, and independent observatories have already begun planning future observation campaigns. Some propose monitoring 3I Atlas continuously as it drifts back toward interstellar space. Others hope to use new generation instruments to replicate Webb's forbidden angle detections with even higher precision. A few dream of launching a flyby mission, a spacecraft that could approach the object directly, photograph it, scan it, measure it up close. But such a mission remains years away. 3I Atlas is already accelerating beyond reach. Its path will soon carry it back into the dark. Once it leaves the inner solar system, the opportunity may not return for centuries. Yet, even if the object itself escapes our grasp, the mystery it revealed will not fade. Researchers are already scanning older sky survey data for faint imprints of similar anomalies. If forbidden angle reflectance is not unique to 3I Atlas, then other objects in deep space may share the same impossible signature. The next detection would confirm a pattern. The pattern would confirm a phenomenon. And the phenomenon would confirm a new chapter in our understanding of light. In the coming decades, humanity may build instruments designed specifically to search for forbidden angle behavior. Space telescopes tuned to detect photons returning from impossible paths. Optical arrays capable of mapping hidden geometry in distant objects. Technology born from a single paradox discovered by Webb. Technology shaped by light from an interstellar traveler that refused to obey the rules. But beyond all the science, beyond the engineering, beyond the mathematics, the mystery of 3I Atlas forces us to look inward. It challenges our assumptions about what is possible. It reminds us that the universe still holds secrets that wait quietly in the dark until we are ready to see them. Secrets revealed not by noise but by precision. Not by chaos, but by geometry. Not by fantasy, but by a single returning beam of light. In the end, this story is not about an anomaly. It is about discovery. A discovery born from a question that should never have existed. A question carried by photons arriving from angles that do not belong to our world. A question that now echoes through laboratories, observatories, and late-night discussions across the planet. What else in the universe reflects light from impossible places? What other shapes wait beyond the reach of our instruments? And what will we learn when the next object bends geometry again? For now, 3I Atlas continues its silent journey toward the edge of the solar system, drifting through the dark with a geometry we cannot see but can measure, reflecting light in ways that break the rules of the world we know. And as it fades into the distance, it leaves behind a final, lingering thought. There is more to reality than the angles we understand, more to light than the paths we can trace, more to the universe than the dimensions we call home. One object, one paradox, one impossible reflection. A reminder that the cosmos is still far larger than our imagination and far stranger than our rules.